So here are our panelists for the event. I've got Milen Todorakev. He is our corporate metrologist working in our primary lab at Fluke Park here in Everett, Washington. Michael Johnston, who's the software product owner for a lot of our calibration software products. Bill Gaviria, the RF product manager, electrical product manager, and Marty Kidd, who's our regional product manager for North America and responsible for electrical and RF. With that, I'm going to hand it over to Milen and let him get started.
Hello, everyone. As Wally mentioned, my name is Milen Todorakev. I am the Fluke Primary Laboratory calibration metrologist, as well as I'm technical manager here at this lab. And I'll be talking about traceability and also like to address a topic called NIST numbers.
1 second, Milen. Let me see if I can't get you over to get you the controls. Something's not working the way it was yesterday. I'll just click through it for you, okay, Milen?
Yeah, please. Can you advance a little bit one more time?
Yeah.
So to really address the topic of NIST numbers, we need to look at a simplified traceability diagram as it pertained many years ago. We had 4 layers of traceability, traceability going up, and which also drives calibration workload. So the top layer in our case, this is for United States, would be NIST, which will be the top layer of traceability. We can think of it as a black box, and whatever happens, how they get their traceability didn't matter. And so it became customary for people to think, okay, you have a calibration from NIST, and you can provide the NIST numbers, and that's of importance, and that's the only way of getting it. So under that kind of a structure, and with lack of trust in with other NMI, it just became the norm that everybody in US will get their traceability from NIST, and likewise in other countries, they'll be getting it from other advanced national metrology institutes. With that, it became a tradition to ask about, please provide these numbers. Well, let's go to the next slide, please. So the traceability for the Fluke Primary Lab, we have been accredited many years. Our accreditation was the NAV Lab. Wally, can you please advance? Yeah. So NAV Lab is the choice of the primary lab because we historically have served mostly high-end customers and exclusively research in government and Department of Defense. So at that time, it just made sense that NAV Lab being under NIST, which is also US government, our customers were really satisfied with that kind of traceability path. And with Fluke being a global company, it was a burden for customers. Anybody buys equipment from US in Europe, they, because of lack of trust into calibrations performed in other countries and no cooperation between NMIs in different countries, or rather a documented relationship that people can look at. Anybody buys something in Europe, they immediately have to go and route it for calibration to a different calibration lab that's traceable to local NMI. So at some point, Fluke decided to ease the pain of these customers, and we were accredited through DKD, which is the lab equivalent of NIST in Germany under PTB. So that was a little bit difficult to maintain 2 accreditations. Obviously, there would be differences of how you prepare for each audit. It's not exactly equivalent. And so we kept with DKD accreditation for many years until Wally, can you please advance? Until we had the ILAC MRA. ILAC is an international organization, and MRA stands for Mutual Recognition Agreement, which basically enabled international equivalence of measurements. With the signatories of MRA, now we have equivalent rules for accreditation labs, and also with that we had the means of starting to do comparison between NMI, and so that improve the equivalence between these labs. Can you please advance, Wally? So under this new structure, the structure of calibration hierarchy, or the pyramid I was showing you before, now has 5 layers. So the top layer is no longer an NMI, which is a black box, but is actually the SI units. So in this new diagram, everybody points to it, and you can see that we have the generic national lab in layer 2, and we also have BIPM. So the BIPM, it's the International Bureau of Weights and Measures in France that actually oversees and has a really good website where one can go and actually look up comparison between different NMI. So with that, we have now a lot of trust that the calibrations in different countries and regions laboratories that fall under the MRA now have equivalent measurements. So with that new structure, one have to understand that a company like Fluke, we get our traceability from at least 4 different NMIs. So when somebody calls and asks for NIST numbers, it's just impossible to provide that. And we refuse to say that we are traceable to numbers that, if one looks on the NIST website and NAVLAB website, there is actually a discussion on the NIST numbers, and what they say is that those are purely for administrative purposes. They were never a proof of traceability. So I hope that that with this presentation, it will become clear why we can never provide those. For more information, there's a link on our Fluke Cal website that we actually have a statement from our corporate metrologist on the NIST numbers stating just that we're traceable to the SI units. Can you please advance, Wally? And as the last slide in my presentation, I would like to actually show how we are traceable for one of our flagship calibrators in our manufacturing facility. So what I have here on the bottom layer is all different 6 functions of FIT 730. And going vertically, I show how we go to different places. So on the DCV, we are traceable to the SI through a Josephson voltage system. In the early 90s, Fluke acquired a Josephson system, which is a NIST design. And so we are traceable, we are realizing the volt through this system. And although this is an intrinsic standard, Fluke participates every 3 years in a North American interlaboratory comparison, where everybody that owns the system in US and Canada can compare their results. And believe it or not, being an intrinsic standard does not guarantee you're getting the right answer with uncertainty claim. So our uncertainty on that system is 5 nanovolts per volt plus floor of 50 nanovolts, which when one measures a Zener, a 10-volt Zener, would be equivalent to 0.01 microvolts per volt, or as some people still refer to ppm. The rest of the functions for AC voltage, we are traceable through a 792, through NIST, and then resistance. We have mixed traceability currently, NIST, and also going to Canada, NRC. For DC current, it's a combination of through resistance and DC voltage, which is our JVS system. And for AC current, we have been exclusively traceable through PTB. through a series of A40B shunts, as well as multi-junction thermal converters. And for some functions, we go through other created lab, which example is the frequency measurement in our lab is created through the Fluke Service Center, which owns a FMAS NIST system. So I hope with that, I can even more stress out that there's no real NIST numbers traceability, and it's just traceability to the SI. And that concludes my presentation. Thank you. Wally, back to you.
Again, thanks, Milen. For those of you who have questions, please place them into the chat window. And again, as at the end of the seminar, we will follow up to everybody with a copy of the slides and a link to the recording of the event via email. The next person that we'll have talk is Michael Johnston. And Michael, are you unmuted? Let me get him unmuted real quickly. There, Michael, are you able to talk? How about now? Michael? There you go. Michael, can you speak? Hello, Michael. Let's just work our way to unmute. Now you're unmuted, Michael.
One second.
There you go.
There we go. Okay.
All right, so Michael, I'll let you take, was having difficulties passing the baton, so I'll just control the slide in advance if that's all right. And we'll let you go from there.
All righty. Thanks, Wally. So as Wally mentioned, I'm currently a software product owner for most of our calibration products. But prior to this, I actually worked on the technical support team for our electrical hardware. So that's more where my background came from, but I've moved into the software side. If you want to go ahead and advance, Wally. So I spoke with Krista Erickson, who probably a lot of you have spoken with on the technical support team, and asked her what a good topic for this roundtable would be. And she mentioned NPLC and read rates and aperture as something that she could questions about. So that's what I wanted to address today. So NPLC it's an acronym, and it stands for Number of Power Line Cycles. So it's based on the line frequency that your specific instrument is operating on. So for us in the United States, that's typically 60 hertz. Elsewhere, that's 50 or 60, depending. And so what this does is it bases the speed at which and the rate at which you are taking a measurement on the power line frequency. So it's triggering off of that and cycling off of that. So depending on what your power line frequency is, that time that it spends taking a measurement differs for the same power line cycle setting. So one power line cycle is essentially the inverse of the frequency. So operating at 60 hertz, that's 0.0167 seconds for one power line cycle. Comparatively, at 50 hertz, that's 0.02 seconds, so it's a little bit longer. That calculated time is really called your aperture. If you're familiar with photography at all, an aperture setting with photography is how wide open your lens is, and that changes the amount of light that's captured when you take a photograph. So when we're talking about measurements, our aperture is how much time we spend looking at that measurement cycle. And so depending on what our aperture setting is, it can pick up more or less noise when we're looking at an AC signal. So when we talk about power line cycles, we're really looking at an aperture setting just in a different term than the specific time. And the instrument taking a reading every n power line cycles when you have it set to a specific number of NPLC. If you want to go to the next slide, Wally. So why are we using NPLC as a setting for aperture instead of just doing it directly with time? You'll see in the chart on the left, what this demonstrates is that the maximum noise rejection when we're looking at a signal occurs at multiples of that power line frequency. And so since the settings are in terms of that power line frequency, it's dynamically accounting for the differences to achieve that noise rejection. What that allows us to do is it doesn't matter for me whether I'm in a 60 hertz power line system or 50 hertz. If I'm setting it based on the power line cycle number, then it's always going to match up with a multiple of that. And so that allows us to very simply account for that frequency. And even if it's a little bit off of that nominal frequency, we get that maximum noise rejection. That's really why that's such a commonly used term in electrical measurements. Go to the next slide. We're going to look at some of the examples from Fluke equipment and how we're setting those different aspects comparatively across a few of our instruments. So starting with the 8846, our read rate is determined by an NPLC setting, but we're limited to the specific values for each. So depending on the range and the function that we're using and the resolution setting, we have different options for what we can set that NPLC value to. And is we get additional error as we go into those faster read rates. So the narrower our measurement window is, it introduces additional error, which we can expect because we're not getting as wide of a picture. We're not getting as much light in, if we're going back to the camera example, to be able to differentiate between noise and the actual signal. So 8846 is kind of a good middle of the road instrument in terms of what we can set. There's a little bit of variability, but it gives you a few options, but very simply to set it just based on NPLC. If we go to the next slide, we'll look at the 2638. So it's very similar to the 8846 in the way we configure this. The 8846 and the 2638. The 2638 is a data acquisition unit, and it really shares a lot of the same characteristics as the 8846 in terms of how it takes measurements. And so similarly with setting of those read rates and the aperture, this is going to be very similar. The read rates overall are going to affect the number of readings you get in a long-term scan. And then as you add more channels, because unlike the 8846, this is a multi-channel instrument, so you have multiple readings being taken in a row if you configure it in that way, that's going to affect the overall read rate outside of what you get when you set your aperture. So there's a little bit of difference here in what you actually get out of a specific NPLC setting, but the overall concept is the same in terms of each individual measurement. Overall, you have maybe a longer or shorter read time than just a single channel instrument. So if you go to the next slide, we'll look at the 8508. So the 8508 is actually a lot less configurable than the first two. So in a lot of cases, we only have one option for our read rate or our aperture setting. And the max we have is two. So we have a normal and a fast, and those are specific read rates. So that's correlating to the inverse of that NPLC setting. So we're doing this actually as a time that it's taking the measurement. But in this case, there's no configurability. It's just, it's this or that, or it's just this. And again, similarly, there's additional errors that get introduced as you take that fast reading approach. But because the differences are fixed, it's a little easier to know what to expect than when you have a more variable approach to configuring that. And if we go to the next slide, so the 8588, which is our newest meter, incredibly adjustable in terms of this. So aperture can be configured directly based on either an NPLC setting or an actual specific aperture time. And so what this does is it allows you to really fine tune your noise rejection to get your best measurements based on the specific application you're performing. Our read rate is going to be that aperture setting and then added to the delay between readings. So when we're taking multiple readings in a row, the 8588 and the 8558 allow you to set a delay between readings, and that influences that overall read period that's taking place. But the aperture setting is where that really comes into play as far as the noise rejection and getting that set. So across those different examples, even just within Fluke, you can see a lot of different, a lot of variation in how you configure those settings. But ultimately, that aperture setting, whether it's set as a time or a fast or slow or a specific MPLC setting, all of that goes into determining the noise rejection for your measurement. So it's an important thing to consider when you're looking at precision measurements, and hopefully that cleared up some of the differences and maybe what are similar that may look different across our instruments. I believe that was my last one.
Thanks, Michael. That was useful. Again, as you have questions, please type them into the chat window, and we will try to queue those up towards the end of the session and answer them there. Next, we've got Bill Gaviria, and so Bill, I'm going to unmute you.
All right, I'm unmuted. Hello, everybody. I'm Bill Gaviria. I'm the Electrical and RF Product Manager. I'm going to talk real briefly about some of the RF measurements and some of the mathematics associated with that. Wally, am I under control or you are? I think Wally is under control.
Yeah, Bill, I've got the control.
Okay, so next slide, please. So what I'm going to talk a little bit about is kind of give you the difference between some of the AC and DC measurements, or known as the DC and LF, and some of the microwave. You know, some of what are the differences, you know, why we do this, and we're just kind of going to take you from DC to microwave and beyond that. So next slide, please, Wally. So in DC and low, we use Ohm's law, and it's pretty simple. We go from one measurement to another. We use very typically the voltage, and we make measurements in volts and microvolts up to about 1 kilohertz. We also use the current, amps and microamps and so on. We have different values and standards for that. And we also do resistance, we do ratios front to back, we do a percentage, we do a lot of the parts per million. And then in the new world, we use microvolts per volts, and you'll see a lot of changes in specifications. And now we get into a little more complex measurement. Now we start using, instead of just the simple Ohm's law, we kind of use, you know, power square or voltage square or ratios and that. So we kind of just move you through the next generation. And now when we look at the microwave side, next slide, Wally. We really start getting into a little more complex numbers, and they're complex numbers because we now look down a transmission line, and there's a lot of things that affect a transmission line, whether we have adjacent power, whether we're looking at reflection coefficients, whether we're looking at BSWR, whether we're looking at what's called S parameters. And this is how we look at a transmission line, and we understand whether most of the power is being absorbed by the load on the other side, or some of it is being reflected back to the generator. So the Smith chart on the top really tells you that. It is a very old chart, invented back in the 1800s, or I'm sorry, about, I think it was 1947, and it just kind of it's evolved it's made a couple of changes, but it's basically the same. And it really looks at the load and the reflection of the load back to the generator. Next slide, Wally. So in microwave and in RF, we use the decibel. And as you can see, it was invented by, or it was actually at Bell's laboratory, invented by Alexander Bell. it stands for 1/10 of the value. In microwave, in an RF, we use very large numbers. So instead of, using something like e⁻⁶, we'll go ahead and call a dB, or we'll use a different type of measurement. We use the scale, and that scale is a power ratio. And that power ratio is in a logarithmic scale, which is a base 10. So it is a ratio between a input and an output. Next slide, Wally. So in here, what we can see is that the power ratio is the value from P1 to P2. So I have an example there that if I have a 200 watt and P2 is equal to 100, we can calculate what the dB value is. It's very simple. The P2 will always be the reference, and the P1 will be the other value. And to go back to the other, we use the logarithmic value. We just simply use that same formula, but we just manipulate it a little bit, and we convert it back. And now we can just go back to the power. So it's pretty straightforward. It's pretty easy. And again, it's only used because of the large values that we use in RF and microwave. Next slide, Wally. So here's an example of what we do in power and in voltage. When we talk about power, we talk about the 10 log. When we talk about voltage and current, we talk about a 20 log of value. So you can actually just kind of be able to look at these values. One is proportional to the voltage square, and the other one is just a simple 10 log formula. So if I have a simple 3 dB attenuator, although it is reducing my power by half, as you can see in the example 1, a 3 dB attenuator is half power, or one the voltage square, or what we call the 707. So when I'm looking at a bandwidth of a scope and they talk about the half power, they're talking about the 0.707, and that is why most filters, bandwidth of scopes, through pass-through devices, the most important measurement that you make is the half power, because that's where I'm losing it. So it's very simple to say, if I have a 3 dB and a 3 dB, I can just simply add them and I get 6 dB. But what happens to the power? You can't just say, oh, well, it's half of the power. So there is a slight little variance in that. So this is basically where, now we start looking at some of these ratio aspects. So it is a lot easier to talk in dBs, because in dB measurement, I can either add them or subtract them. While if I look at power, I really have to start using my 20 log formula. Next slide, Wally. So why is the dBm? So we have a dB. It is just a ratio from the front to the back, and it could be from an attenuator as a loss, or it could be an amplifier as a gain, and it's all in dB. Now, when we talk about a dBm, now we're talking about a measurement that is based to 1 milliwatt. So now I have a reference. A useful reference is 1 milliwatt into 50 ohms, or 0 dB. And that just kind of gives me a base of an absolute measurement. One's absolute, the other one is a relative. So this is really relative to a 1 milliwatt. And that, as soon as you say 1 milliwatt, you're speaking into dBm and not dB. So, and an example of that is if you purchase a generator, it'll say, plus 20 dBm to minus 140 dBm. So that's the dynamic range, but it's dynamically ranged to 50 ohms or 1 milliwatt. So that kind of gives you a perspective. You also have transmitters that can produce very large amounts of power, like 10 kilowatts. and megawatts. So now you look at plus 70 dB. So it's a lot easier to say a 70 dB than when you talk about that. So you start looking at a different dynamic range. You look at a mobile base station, and a mobile base station is where the signal comes in. It just kind of gets transmitted when you make a phone call. And those are typically in the range of 20 watts. And that's kind of why you're really limited, or you see a lot of stations around. It is the amount of power that is the limitation of that. If you look at your home or your office and you have a Wi-Fi, that's typically now, instead of you looking at, 10 kilowatts, you might be looking at minus 70 dBm or 100 picowatts. And that is now around your house. So you have the 2.4, the 5G, some is faster for gaming, other is just faster for communication. And that's really what you're looking at. So limitation is really the device in there. And that is probably why you have networks inside your house where you can have a mesh network, and you can put different satellites around your house, you can have a better reception. So if we're looking like at absolute thermal noise, we really start talking into the 1 hertz bandwidth, room temperature, noise floor. Now we're looking at minus 174 dBm. And again, because it's all reference. So you see that all these instruments that you see on the right, they're really based off of 1 milliwatt. So that is very crucial for you to understand, that when you talk about a power ratio, you're talking about dB. When you're talking about a dBm, you're talking to a ratio that is referenced to 1 milliwatt. Next slide, Wally. So there's a very big difference. I wanted to put this table on here because when we say 0.1 dB equals 1% or 100 ppm, that is naturally an approximate measurement. Now, if I bring that scale down and I say 0.01 dBm and I say 0.1%, now I've moved that from 10,000 parts accuracy to 1,000 parts accuracy. So very huge difference. Now, in that same respect, if I give you a measurement that I say it is a 1 dB, it might be, if I say 1 dB plus or minus 1, it's not as simple as we do it in the voltage side, because remember that now we're talking a logarithmic scale. So that rhythmic scale may be high on one side and low on the other side. So power factors like this will help you, or these types of charts will help you look to see where you're speaking about. So we'll do the 1 dB. So it's about 25.9% one side and 20.5% on the other side. So very huge differences to understand that. So there's a nice little scale here that can move you on. Next slide, Wally. I got about 2 minutes left. So the other very important measurement that we make is the DBC, and that is the C stands for the carrier. So when I'm calibrating a spectrum analyzer, I might make a measurement that is 10 dB, but when I talk about a harmonic noise, I'm going to make that measurement based on a carrier. So I have X frequency, that is my carrier, and then if I want to look at any noise from it, I look down from the carrier, and that is called a DBC. So that's where I start looking for my first order harmonic, second order harmonic, or my noise floor. So it's very important that on a spectrum analyzer, when you're measuring harmonic noise or spurious, you're talking about DBC, and that is based on a reference to a carrier. dBm is reference to 1 milliwatt, and dB is a ratio between the front and the back. And that is about the time I have, and I could probably go 4 hours. So Wally, over to you. Thank you. Gracias.
Thank you, Mike, or Bill. Our next speaker is Marty Kidd. And so Marty, I'll get you unmuted. And then we'll hand it over to you.
Okay. Can everybody hear me?
All right, Marty. Marty, I'll control the slides, all right?
Okay. Thank you guys for joining us. My name is Marty Kidd. I'm the Regional Product Manager for Electrical and RF for the US and Canada. I'm going to be talking about how to select the best calibrator for your workload. You can go to the next slide, Wally. So the first thing, you have to understand your workload. You have to know, what do I want to calibrate? What do I need to calibrate? Most people that come to me looking for a calibrator, excuse me, they want to do a lot of handhelds. They have a lot of handhelds. They'll give me some models, but then they'll throw in some other things. They may have some scopes or some other oddball test equipment. Maybe they got some clamp meters, current clamps, those kind of things. First thing you want to do though is understand, what is it that I need to calibrate? And then how am I using this? Do I need to calibrate it to manufacturer specs? Do I have a specific way I'm using this equipment that I just need to calibrate to meet that need? I have had some customers that were working in a electrical distribution meter shop that they had a wide variety of DMMs, but they really just needed to calibrate at line frequency and, you know, continuity, resistance, current, everything at like nothing above 100 hertz. And in that case, there's a different calibrator that you may be able to use rather than going for a fully loaded multi-product calibrator that can do everything. So understanding your test equipment, your workload, and understanding what, how you're using it and how you need to test it is very important. And then, what other workload is there? Is there other workload that you're sending out for calibration that you could calibrate yourselves if you had the right piece? Do you have scopes? Do you have some different panel meters or other test equipment that is calling out a calibrator? Next slide. So the one thing that I would do if I'm looking to evaluating my workload is I'm going to go to the service manual or the operator's manual and look for a calibration procedure. And at the start of that calibration procedure, there should be a list of test equipment required to do the calibration or testing, performance testing. So here's an example. I think this is from the 187 or 287, I'm not sure. And basically says, hey, it's calling out a 5520A with the scope option. And it not only calls it out, but then it shows the characteristics that you need. So it shows the accuracy that you need, the frequency ranges, for the different parameters. So this is a way that you can look at your workload and say, okay, here's what it's calling for. And then you can evaluate what calibrators are out there that offer these parameters and accuracies that I require. That goes a long way to knowing that you don't need a 5730, that a 5502 can meet your needs, and there's a huge difference in price. Okay, we can go to the next slide. We do have a electrical calibration workload matrix. There is a link listed here on the slide that will take you to this matrix. It's helpful. It's not everything, but it does help understand which calibration standards can do what. You can see the 5080A is good for high burden, better than any of the other products that we offer. It's not that accurate, so it's only saying up to 3.5 digit multimeters. It also only goes up to 1 kHz. So great for electrical meter shop, great for some manufacturer that just wants to do basic testing because they're using it around line frequencies, but probably wouldn't work for someone that wants to do, for example, an accredited cal on a 287. It's not going to get to the frequencies you need. The 5502 does a much better job, can handle pretty much any handheld multimeter. The 5522A easily handles all the handheld multimeters, can do some of the process calibrators and even some of the 6.5 digit DMMs. And then of course the 5730A is what you would use for really any benchtop type DMM. Now there's also all kinds of other special applications where you need the accuracy of a 5730A, and that's where understanding your workload and the actual test requirements allows you to go in and compare specs. And you know, some people can do this very easily and know how to do it better than I do. Some people are not sure at all what they need, and they're more than welcome to call somebody like myself and say, hey, I need help with this. What would I need? You can also see that 5322A, something that does electrical testers, but can also do some basic handheld type functions. And if we go to the next slide, Wally, we see a little more about what can do when you want to do thermocouple simulation or measurement. There actually is a pressure option with the 5522. And then you can also see with scopes, the various options that are there for the oscilloscopes. A lot of people will get a multi-product calibrator with the scope option because they can cover all their workload, but they have to have enough workload. If you only have 2 or 3 scopes, I'm not going to recommend that you get a scope option. It's not, you don't get the payback for the investment. And then next slide. And then this talks a little more about the power and energy. So we do have some power and energy capabilities with all of the multi-product calibrators, outputting both current and voltage at the same time. We also have the PQ option on the 5522A, power quality option, which does some flicker and harmonics. But really where we address this is mostly on the 6003A, 6100 series power and energy calibration standards. And then of course, if you're doing clamp meters, there's a number of ways to go about it depending on the ranges you need. Any of the multi-product calibrators get you to 20 amps, and with a 50 turn coil, you're now at 1000 amps. If you need to go higher, you can look at using the 52120 in combination with any calibrator, although it will work closed loop with the 5730 and the 6000 series. And I think that's it. Do we got one more slide? I can't remember if we do or not. We're on Q&A. We got 6 minutes.
Thanks, Marty. And I appreciate all the panelists and their discussions this morning. Let's open up, let me open up the chat window and see what kind of questions that we've got here and see what we can do. So I've had several questions about, can we send the presentations to my email address? We will be taking, this session's recorded, and we will be sending a link to the recording as well as a link to the presentation that you can, we'll be sending that to you via email, and you can go and pick up the presentation as well as a link to the recording at your leisure when you feel comfortable doing so. Let's see where, let's go up closer to the top. There was a question about traceability to current coils. Maybe I should open up and unmute all of the panelists at this point. It might be a little noisy. So all of the panelists should be unmuted at this point. Does someone want to take on the question about traceability for current coils?
I guess I'll participate. Yes, current coils, we recommend that the current coil be calibrated initially, which it does. And after that, there's a A2LA letter that says that since it is it works on the Hall effect, a one-time cal is valid enough, and that is it. Now, if you abuse the coil, which means you exceed its rate, its duty cycle, then you should actually have it recalibrated.
And Milen, how do we provide traceability for that calibration in the primary lab?
So the traceability is through different transfers from a single coil that's monitored by A40B shunts. So essentially it goes to traceability from ACI as well as Decibel, which indirectly it's traceable to resistance and Decibel, which on the Johnston system.
Okay.
It's a very complex process for transfers where we can characterize a current clamp, and then we can measure a output on coil. And just to add a little bit more on Bill's answer, it does not need to be recalibrated unless it's severely damaged geometrically. We've seen some that come flat. Chances are even with physical damage, it still performs well. We've seen that, but you can't rely on that. So if it gets dropped and it gets marked, it needs to be checked and repaired.
Okay. Michael, I've got a question here talking about instantaneous readings that has less noise when sampling at multiples of the power line frequency or the average value of multiple readings. And I think this is, and if I'm interpreting this question, I'm assuming you can see it too. It's a little bit of a confusion about, multiple samples and averaging versus the length of the sample aperture to begin with. Can you provide a little bit of information?
Yeah, so I can't see that question. I seem to have misplaced the chat area. It's really two different ways of handling noise within a signal, right? So when we talk about the aperture setting, we're looking at the noise within an individual reading. When we're looking at averaging multiple readings, we're taking that noise away by averaging multiple readings. One is not necessarily better than the other. As a mathematician, I would say that we want every individual value to be as close to accurate as we can, and that's going to provide you a better overall result. Because the issue is if you have a lot of noise and you're averaging multiple readings, you could still end up with an average that is off from the true value. So using an appropriate aperture and taking a longer reading is going to give you the better result overall.
All right. I have a question here about what type of measurement methodology do we use to verify CJCs, cold junctions, and how do we use calibrated thermocouples to accomplish this?
Can you repeat this question, please?
What type of measurement methodology do we use to verify CJCs, cold junction compensators? And how do you use calibrated thermocouples to accomplish this?
So in general, we do not calibrate cold junction compensators in the primary lab. I believe that some work is done at the service center about that. The primary lab actually does super characterization of thermocouples that are used with our multi-product calibrators.
Okay, I happen to know a little bit about this. The way with a cold junction, what we do typically is we connect it to a lag bath via relatively short thermocouple wire. And then we're expecting there to be very little to no variation between the junction and the lag bath. And at that point, we should be reading pretty close to the temperature of the lag bath as a way to validate that.
And remember that the processor in there is mathematical. So all the tables, if you check like K and S, everything else is converted mathematically. So that's an important point.
Okay. I am at the end of the chat window and don't see any more questions here. I may have missed
Well,
some.
if you look in the Q&A area, are you able to see that? Because there's some in there.
There's,
too.
all right, let me go roll over to there. There we go. We'll get to that section and see what I can find. I'm scrolling through, I see lots of discussion. One of them, is there a way to slow down the capacitance readings on the 8588?
I believe Michael answered that.
Yeah, I
Okay.
responded in text, but just to touch on that. So capacitance is a bit different than a lot of the other functions. It doesn't have a specific aperture setting. It's all built into the way that the ramp signal occurs.
There's a question on how often do instruments need to be calibrated?
Generally speaking, we recommend 1 year cal interval. There, in some cases, there may be a specification for 2 years, but generally, you're going to base it on the specifications of the instrument and your own quality system.
This might be a good one for Milen. Milen, Fluke sells measurement calibration devices as well as calibration lab services. 17025 demands separation between these concerns. How does Fluke avoid a conflict of interest between equipment sales and laboratory services?
So laboratory, so by that question, is that meant that we sell like calibration stations?
It says, I think it says, 17025 wants to separate the service for providing calibration from the manufacturing of the equipment. In other words, they don't want us to link the two. How do we avoid that conflict of interest?
Well, I don't really think we sell services. If that's the question is more specific, I'm thinking that probably has to do with the DVMP, the direct voltage measurement program, where we send traveling standards 732. The reality is that has actually been reviewed, and I don't think that the accreditation body found any problems with the service.
I also
it's
operationally
it's not really a PT service.
Okay.
Hey, baby. What do you got there?
Okay, I'm at the
That's nice.
Mark. You're on. Your microphone's on.
There you go.
Okay, guys, I think we have reached the end of the questions and end of time. I want to thank everybody for joining us this morning. We hope that you found this to be a useful event for you. We want to thank you. We provide other ways to stay in contact with us, and if you're interested in hearing more from us in the way of bulletins, more seminars, or other information, there is a spot on our website where you can connect to us and then manage what information you'd like to see from us. So please take advantage of that if you're so interested. And again, I want to thank you this morning for your time, and we will be sending a link to both this presentation and the recorded web session to you shortly. Again, thank you.
Thank you, guys.
Thanks, everybody.
Thank you.
Thank you. Cheers, everyone. Adios.